Okay, so we're starting the video a little bit late, but we have here this air track on a table. Mass 2 is connected to mass 1 along a string around a pulley. Mass 2 has mass given 20 grams, mass 1 is 250 grams. Mass 2 is going to fall due to the influence of gravity. It's going to pull mass 1 to the right. So far we have a free body diagram drawn for mass 1. Now we are looking for an F-net formula for mass 1. So what's the F-net formula for mass 1? What are all the forces involved vertically? Do they cancel out? So we don't even have to worry about the vertical forces. So let's just think about the horizontal forces. So F-net horizontally is tension, and tension only. It's the only force horizontally. So in these problems, typical of these problems is you only have to really worry about one dimension at a time. You don't have to worry about the vertical dimension because they're balancing out. So this F-net is in the x direction, but I don't have it labeled there, but I mean you could. You say F-net x. This is the net forces in the x direction. So what does F-net get replaced with? MA. Okay, and do we know M? It is what? 0.25 A equals T. Okay. So there's our first equation, our first constraint. And we're going to do this problem with two simultaneous equations that we'll solve with a system. So now all we have to do is draw the free body diagram for mass 2. So what does the free body diagram look like for mass 2? Is there any horizontal forces? No, but there is a vertical force. So there's a force of gravity for M2, and there's something opposing that, which is the tension going up. So let's get the F-net formula for these vertical forces. Which one's larger? We know that the gravitational force is going to be larger because we know that this is going to pull down. So this force has to be larger than the tension force. So because it's larger, we'll start with it. Always start with the larger one. And when you think about this here, like which force is driving the acceleration? The gravity. And which one is trying to hinder that? What's trying to stop that from happening? The tension. So because it's opposing it, you keep that one minus. Now what's the next step on this? We always, once you get all the forces involved, then you switch F-net to MA. And in this case, M is 0.02 A equal to, and what's FG going to be? 0.02 times 9.81 minus T. So let's simplify that. What's 0.02 times 9.81? We have 0.1962. 0.02A. Now what's nice here is we have a formula for T over here. See this formula for T? We could put that right there. And then we'd only be dealing with an equation involving A. So we'll do a nice little substitution. Collect like terms. So I'm just going to add this to the other side. And we get 0.19 0.27a equals 0.1962. Divide out 0.27. And you should get your acceleration, which is 0.726 repeating meter per second square. And I apologize for running out of room down there. Do you want me to zoom in a bit? So after I substituted in t, it's just some basic algebra. Okay, so we have the acceleration now. So what can we do now that we have the acceleration? Substitute the value for a back into the system to get the value for t. And do we have a nice formula for t? Yeah, from the first body. It tells you exactly that tension is m1 times a. So you just have to times this value by m1 over here, and you'll get 0.25 times that answer, 0.726, and you'll get the tension. Okay, and then getting 0.182 newtons. And I apologize for running out of room. I spent most of the space just drawing a nice picture and left no room for the math. Okay, so this is treating the problem one body at a time. If you treat the problem one body at a time, and you're only going to have two body problems, so you're only going to have two equations, two unknowns. If it was a three-body problem, then you'd have three equations and three unknowns. Four-body problem, four equations, four unknowns. So this isn't always the most efficient way. It's decent when it's only a two-body problem. Okay, so what I want you guys now to do is try the one in the workbook. That's identical to this, just different numbers. So in the workbook, it's on page 95. Okay, so there's two questions on page 95 that I'd like you to try. Okay, so these two problems here. Start with 16, please. Even though there's a disk, it doesn't matter. You can still do this one. Okay, so we're going to start with 16. Very similar question. I want you to draw two free body diagrams. Okay, I want to see two free body diagrams, and I want to see two F-net equations. Okay, so this is your goal right now. Two free body diagrams and then two F-net equations. That's your goal right now. We'll spend about 15 minutes on this page, then I'll show you another problem. It's pretty interesting. Yes, I would like you guys to try this problem now. So you could jot down the problem in your notes, and then draw a diagram, draw a free body diagram, get your F-net formula, see if you can solve it for the acceleration here. This one's interesting because it gives you a piece of information that you have to decide how to use it. So it's just two buckets of nails, and they're connected by a rope, and they're hung vertically. Yeah, that's a good observation. I'll draw you guys a picture. It's basically like a 5 kilogram pail and another 5 kilogram pail. Yeah, it's exactly it. You treat the two masses as a single mass, yeah. Okay, and then the tension in the rope connecting the buckets is 60 newtons. So the tension in here is 60 newtons.
Yeah, I was just going to ask, is everything, would all the tension be 60 then?
No, the tension in the rope here is different than the tension in the rope here.
Because if everything's moving down, then don't all the forces change for each bucket?
They're being pulled up.
Oh, they're being pulled down.
Right here, they're being pulled up. So draw a free body diagram for the buckets.